Had a little bit of trepidation when I realized Josh was going to be introducing me, but he was very nice, so I appreciate that. So I'm going to wrap up today by talking about something that has plagued us in software for a long time, which is the ability to support constant change. Because the world we live in is constantly changing, and there are ways that we can better support this idea of constant change. So if you look in Merriam-Webster and look at the definition of change, you see lots of different ways to think about change. A lot of these talk about direction and going different, for example. But for us, there are really two interesting aspects of change that we deal with on a regular basis. And one of those is business-driven change. And this is a thing that we've really been focusing on in the software world for the past 20 years or so. The ability to change requirements when one set of requirements changes because the market's changed or because we're changing the way we do business, or we merge with another company and we have to take on all their stuff, and so we have to deal with that kind of change. And in fact, most of the books written about change in the Agile world have been written about this kind of change, this business-driven kind of change. And we're gradually getting better and better at this over time. We incrementally learn how to do this a little bit better. But the kind of change that has really plagued us, and we've been less well at handling over time, is this technology-driven change. It's the kind of change that happens to us whether we want it to or not. Because one of the problems that we have, particularly in architecture, is that, and in big corporation and design and enterprise architecture in particular, is we seem like architecture is like an equation to be solved. And if we can ever just solve the equation one time, we can drop the whiteboard marker and walk out of the room and never have to think about it again. But that's not the way our world works. Everything is constantly shifting and changing all the time, because the world we live in is extremely dynamic. So think for a moment about the software development ecosystem. This is all the tools and the frameworks and the best practices and approaches, basically all the things we know about building software up until about 10 minutes ago. That is the software development ecosystem that we live and work in on a regular basis. But in the book that we just wrote, called Building Evolutionary Architectures, we characterize this as a dynamic equilibrium. Meaning it makes sense, it's equilibrium, it's not chaotic, but it's also extremely dynamic and can shift and change fundamentally in any way without notifying you. A great example of this dynamic behavior is when Docker hit our ecosystem a few years ago. Even if you're not using Docker yet, it fundamentally changes the kinds of decisions now available for you in this software development ecosystem. And the problem is, this happens all the time in our world. One of the roles that I have is a conference co-chair for the O'Reilly Software Architecture Conference. And at the end of every conference, all the O'Reilly salespeople come to me and say, okay, Neal, tell us what the next big thing in architecture is going to be next year. And I keep telling them, I have no idea. Because the way that's going to come about is one small change is going to trigger another small change, which will trigger another small change, and fractally, it'll fundamentally change the entire world we live in ways we never expected it to. But this is a big problem for some roles in software architecture because they're supposed to do long-term strategic planning. But how is long-term planning possible in a world like this? So over the last year or so, I've been traveling literally all over the world talking to enterprise architects, a lot of our clients. And I don't know a group of people who are more terrified right now than enterprise architects, because slowly their standard playbook has melted away and become invalidated one piece at a time. And I keep asking all of these enterprise architects this same question, and none of them have had a good answer for me. So maybe somebody here over drinks can finally give me a good answer to this question. And the question is, can you tell me with great confidence exactly what JavaScript web framework you'll be using 2 years from now? And of course you can't, because it probably hasn't been written yet. How is long-term planning possible in a world like that? And of course the answer is it's not. But then that begs the question, well, why are we trying to do this long-term planning? Well, you need to do that because change is really expensive and difficult, and if we can plan our way out of it, then we can mitigate that change and difficulty. But what if change wasn't as expensive or difficult? What if you built the notion of change into your architecture rather than constantly being blindsided by all these changes that come about? If you could do that, then now you don't have to have a better and better crystal ball. You've actually built adaptability into your architecture. And now it's not a surprise when change comes. You just adapt to it and support constant change at the architectural level. So two observations are going to kind of drive my talk today. And one of them about architecture is that everything in architecture is a trade-off, including things that you don't think are trade-offs. What that usually means is you just haven't identified the trade-off yet. And let me give you a couple of examples of these things that we never really realized were trade-offs for like a decade until we finally realized, oh, that's actually a trade-off. That's not a good thing purely by itself. Excuse me. So let's talk for a moment about code reuse, which for a long time was viewed as a purely beneficial thing. There's a great quote by John Cook, who does a lot of writing and thinking in the software world, that says that we've been sold the idea that code reuse is like Lego blocks, but it's a lot more like an organ transplant than it is snapping Lego blocks together. It's a lot messier and more painful than you think it's going to be when you set out to do this. But let's talk for a second about two different ways of thinking about reusing code. And I'll start with the kind of retrograde case of the enterprise service bus driven service-oriented architecture. Part of the goal of this architecture was to create this really rigid service taxonomy where all these services up at the top here, these business services, were designed to be the abstract thing that we do as a business. And the implementation for all these guys with these enterprise services down here at the bottom. And then the glue of this architecture was all this orchestration and choreography stuff here in the middle. Because, and people really said this with a straight face a decade ago, what we'll do is if we write these enterprise services to be just exactly reusable enough, there will come a day when we don't have to write any more code, that all new application development will be stitching together new things with orchestrations, and we'll be done with all this messy problem. This, of course, ignores the fact that the world constantly changes and shifts ways, but that was what was thought in this world. And in fact, there was a specific reuse philosophy that pervaded this architecture. And in fact, architects were instructed to look for this pattern in architecture. Let's say you're an insurance company. You have all these divisions for insurance. And you notice at some point, they all have the notion of a customer. And as an architect, you were supposed to notice this and go, hey, look, they all have customer. That must mean they're all different aspects of the same thing. So we should create a single customer service, encapsulate all we know about customer there, and just reference that thing in our architecture. Some of you probably participated in some of these JAD sessions where you lock all the business people in a windowless conference room and deny them food or water until they finally tell us what customer is, once and for all. But that never actually works because you're going to change the business tomorrow, or you're going to merge with another company, so it's always a shifting, changing thing. But this was viewed as purely a beneficial thing because duplication's bad, right? And this eliminates all that duplication that you might have otherwise. And so obviously this is purely a force for good. But then we started realizing, as we kept doing this more and more, that it's not necessarily purely a force for good. Because the side effect of this is, so in this scenario, I have auto insurance. Now, to have auto insurance, you have to have a driver's license. And that's a characteristic of the person, not of the vehicle. And of course, we're going to back this by a relational database with a good dedicated enterprise DBA when you can't have auto insurance without a driver's license. So that's got to be a required field. But the problem is, if I'm in disability insurance, now to instantiate one of these customer things, I have to go dig up a driver's license somewhere. And I don't care anything about driver's license. It has nothing to do with the problem I'm trying to solve. And so the fundamental problem you end up with here is that building that single reusable customer thing means you have to build all this stuff into it to make it reusable. And one of the observations we made in the Evolutionary Architectures book is the more reusable something is, the less usable it is. You build something to be ultimately reusable, but it's hard to use it in one case. This is also known in the software world as use before reuse, because if you build everything for reuse, it becomes really difficult to use it for a single thing. But there's another problem here as well. and maybe a bigger problem. And that is, when you have that single customer service like that, now everything is coupled to that customer service. So if I make a change to that customer service, it ripples out to all sorts of places in my architecture. And that rippling coupling effect, it turns out, is really damaging to architecture if you want to make small changes in an isolated way in architecture. That's the other trade-off you have here, is you not only build too complicated things, but you also end up creating these coupling points that make things like incremental change really, really difficult. And so this is really the trade-off that we realize is reuse versus coupling. And this is actually one of the great revelations, I think, one of the subtle realizations of domain-driven design. Because when he created this idea of a bounded context, he basically said duplication is better than coupling. That was the trade-off that he identified was, you know, sometimes duplicating those things and not coupling them allows you better isolated change. And if your goal is isolated change, that's the better trade-off than creating all these coupling points in architecture. But you know, in software, everything is 2 steps forward and 1 step back. And so one really good thing happened in this architecture, which is around these infrastructure services. Things like monitoring and logging and authentication, authorization, service discovery, all the plumbing parts of your architecture. It turns out it's really nice to have a single representation of all those things. But of course, the philosophy that pervades the microservices world is the one that comes from domain-driven design, where you don't try to create single coupling points in your architecture. In fact, the opposite is true. You try to create things as decoupled as possible. And even if catalog, checkout, and shipping have the same notion of a customer, you never try to reconcile that to a single class. You just send information back and forth through messages. And so the philosophy in this world is that duplication is preferable to coupling. And this untangles all of our domains in a way that you might have minor duplication, but now you have a single unit of change, which is nice. But now we've lost something. Because what about all that operational coupling? So let's say that we make every service team responsible for implementing the correct monitoring and logging and all that stuff. So let's put aside the moment that some teams maybe forget to do that or don't do it correctly. What about things like, I need to update the version of our monitoring tool? How can you possibly get that rolled out in any kind of consistent way across your organization? So we've come up with some interesting reuse philosophies in the microservices world to solve that problem. You frequently see microservices drawn on top of a gray box like this, and that's not accidental. That gray box actually has semantic meaning. This has been called variably either service templates or sidecars. The name has kind of shifted over time. And the idea here is that we have all these common shared operational concerns in microservices, things like logging and monitoring, authentication, authorization, service discovery, circuit breakers, all those things that we want operationally common. So why don't we build a common shared mechanism, either a template that we can subclass from or shared library that each one of our services has. That's this idea of a sidecar. And that led to this idea that you hear that's very popular in the microservices world right now about service meshes. It's this realization that we have all these shared operational concerns that we actually benefit coupling together at the architectural level. And the idea of a service mesh is, well, if we know that every one of our service component has these exact same kind of operational libraries in them, we can actually build dashboards that allow us to wire those things together and change things like monitoring, logging levels, and other sorts of operational concerns. And so what we've managed to do here is couple the parts that we benefit from coupling together, but decouple the parts that we don't benefit from coupling together, which are all these domain classes, which allows us to have the kind of change that we want to have at the level we want to have. Because now we've unified change for the things we want coupled together and broken apart the things that actually harm us to be coupled together. So that's a good example that reuse is really actually a trade-off between reuse versus coupling and a few other things. Here's another one of those trade-offs. And it's something that we refer to in the evolutionary architecture book as the last 10% trap. And a lot of tools and frameworks end up suffering from what we call the last 10% trap, including some very common hot topics right now. So let me describe what we mean by the last 10% trap. And the difference between, a fundamental difference between what we call an evolvable architecture versus an adaptable architecture. So our book was called Evolutionary Architectures, and we thought about adaptable architectures as a name as well, but there's an important distinction between evolution versus adaptation. Because when I say adaptability to a developer and architect, what they envision is the configuration dialog in Eclipse or Visual Studio. That we've built all these possibilities and we've built switches in it to allow you to adapt to all those things. And there's a lot of software that's built to be adaptable where you can customize it with little snippets of code and switches and that sort of stuff, but they all suffer from this last 10% trap. So let me describe what I mean here. So this is based on some experience I had many, many years ago. I worked for a consulting company that did application development for clients in Microsoft Access. And we ended up shutting down that part of the company because we realized that every Access project had the same characteristic. It started as booming success and ended in total failure. We wanted to understand the dynamic of why that kept happening over and over again. So we codified this as the last 10% trap. And so using a tool like Access, 80% of what the user wants is super fast and easy to build, and it's stunning how fast you can get it done. The next 10% is possible, but difficult. Because now you're trying to do something the tool doesn't really natively want to do, but you can kind of hack it and bend it and cheat a little bit and figure out a way to get it to work. Problem though is the last 10% you cannot get to work because you can't get far enough underneath the tool or the framework to make it happen. And it turns out users always want 100% of what they want and they're never satisfied with less than that. Some of you have been around long enough and have enough gray hairs to remember the 4GLs. Remember the 4GLs in the late 90s? These were all the rage in the late 90s. Everybody was doing application development in 4GLs. So whatever happened to them? Why are we not doing development in these platforms now? They all suffered from this last 10% trap. In fact, what happened to these guys, it turns out, interestingly enough, is the really interesting ones became domain-specific languages written on top of third-generation languages like Ruby or Groovy, but taking advantage of metaprogramming and a bunch of other stuff, so you have a little more chance to dip into the underlying language if you want, but it still has limitations because you can't build every kind of application you want in these frameworks. Other things also suffer from this anti-pattern, like every giant ERP package you've ever seen. They're selling you on this idea that we've built the adaptable piece of software. But think through just a second what they're suggesting there. They're suggesting that they've built a piece of software where they've modeled every possible business scenario on Earth and tested every possible business scenario on Earth in every possible combination of all the switches turned on and turned off, etc. I don't know that that's really possible. And so what happens in all these, but it has the same characteristic, it starts out with a booming success because they handle all the easy things first. And then there comes a day when it's not easy to model the thing. And so you either decide from a business, well, do we bend our business toward what the ERP tool wants, or do we just not model that part of the business? Which is why all these things don't end in success, they just agree to stop working. Nobody wants to say it's a failure because people get fired, but we'll just agree to stop working. Well, I think we're done. We're good here. We'll just stop there and we'll say it's good. So what are things that currently have this same pattern of last 10% trap? One of the things that I'm really curious about is all the serverless stuff. And I don't know yet. The jury's still out on this, but it has all the exact characteristics of this last 10% trap kind of platforms. Prototype stuff's great. Oh, it's awesome. Look how easy it is. Boom, somebody else's computer, don't have to worry about it. And then you try to put it in production. Like, oh, latency, oh, startup, oh, timeout, oh, all these other kinds of things. It may be that they build up these platforms and solve a bunch of these problems, but right now it reeks to me of this last 10% problem of really easy to build simple things, but trying to build real things in them, you hit walls that you can't get around. Another big thing right now are these low-code environments. They're all the rage right now, and I absolutely guarantee all of these suffer from this last 10% trap. This is a quick way. So we did this in the 90s. I've seen this movie before, and it doesn't end well. This was RAD environments in the 90s and the 4GLs and the case tools. It's the exact same stuff. Every one of these things are going to have exactly those kind of limitations. And now maybe it's not 10%, maybe it's the last 8%, maybe it's the last 4%, but users always want 100% of what they want. And even if you can build something that works, at some point they all have to be hosted in some kind of environment. And you're going to need some architectural characteristic that environment can't support, like performance or scale or elasticity or something like that, which you can only get by third generation low-level languages and traditional architecture patterns so far. So both examples of things that are trade-offs in our world. So the second observation is that nothing in our world is a binary. Everything exists along a spectrum. And one of the things that I mentioned before that I want to talk a little bit about is rethinking enterprise architecture. I can't think of another role that has shifted more in the last decade or so than enterprise architecture, because if you look at the standard playbooks from 20 years ago, when most of them were written, most of the assumptions they make are completely crazily untrue. Like the amount of time it takes to design things, and spending several years working on a strategy when the entire ecosystem has changed within the first year that you do that. So let's talk for a second about constraint, but what enterprise architects refer to this as is governance. So let's talk about governance for a second. This is the fun thing about words. The origin of the word govern is actually from the Greek word kubernon, which is the same root as Kubernetes. So there's some little trivial factoid for you today. So govern has several different definitions: to control, direct, or strongly influence the actions or conduct of, to exert a determining or guiding influence on or over, or to hold in check. And so a lot of enterprise architects are playing this playbook where governance is about holding things in check and making sure that we look at software as overhead. Because if software is overhead, the main thing you want to do is minimize costs. So that's one of the driving concerns. And so that leads you to, very often, to this sort of monolithic governance model, because this makes sense. If we pick a single platform, single database server, single reporting engine, then we can move, we only have one license, we can move people between those tools on projects, and so that makes perfect sense from a cost-saving standpoint to do this monolithic governance model. Here's the unfortunate side effect of that model. Is that, okay, I'm an enterprise architect, and now I need to implement this monolithic governance model, and now I need to pick a relational database that everybody in the company can use. I have to go to every team now and find the team that has the worst, awfulest, gnarliest relational data problem, and I have to be able to pick a tool complex enough to solve their worst problem. And I have to go to the reporting people and find their worst, awfulest problem, and the integration architects and find their worst, awfulest problem. And you standardize basically on the most complex stack that you need for every hardest problem. And if you're like most organizations, 80% of your projects don't need an industrial strength relational database. They just need a simple place to store things and get them back. But they're dealing with the complexity of an industrial strength relational database because we standardized on that thing. And so the unfortunate side effect of this cost-saving measure is you end up over-engineering everything to ridiculous degrees. And that's really where this idea in the microservices world came from, the decentralized governance model of let's choose the right technology stack for the problem that we have. And so one of the controversial things in the microservices world is let different teams pick different technology stacks if it makes sense for them to do so, because we're not trying to over-engineer everything to death. And excuse me, this actually indicates a shift in our attitude about governance, which is the other definition of governance, which is to serve as a precedent or deciding principle for. And so 20th century governance was very much about managing overhead and cost savings over guidance. So cost saving was the #1 thing. But we've seen a definite shift over the last few years where now it's a lot more about guidance rather than cost savings. And in fact, what we're seeing as a common model in a lot of organizations is this thing that we call Goldilocks governance, which is kind of the spectrum version of this. It's not the binary of one size fits all, or let every 1,000 flowers bloom and let every project pick their own artisanal development stack. Rather, let's pick a few stacks that we know we can standardize on, a simple one, a complex one, and a really industrial strength one, and we'll standardize across those. So let's talk about some engineering practices. One of the ways to support constant change, ironically enough, is to constrain some things. Because if you have a lot of energy going in random directions, then you're wasting a lot of energy. And if you can lock down some of the things that you are not benefiting from having variability, then you can put more effort into going the direction you want. So let's talk for a second about removing variability. And it's actually interesting that the talk before mine talked about Knight Capital, because that's the great example here of automating things. And really the great lesson of DevOps, because what did the world look like before the DevOps revolution? You had operations people running around doing ad hoc work on a regular basis, and things were constantly falling through the cracks. What looks like that right now? And I would say that a lot of architectural governance looks like that right now, because you have architects who are expensive running around doing ad hoc code reviews and architecture review boards and that sort of stuff, but important things are constantly falling through the cracks. So let me talk for a second about, this is the book that Josh referenced, written by myself, Rebecca Parsons, and Pat Quah, Building Evolutionary Architectures. And one of the things that we talk about in our book is this idea of being able to automate architectural governance, taking the same rules from DevOps, but applying it to the architectural governance world. So this is our definition of an evolutionary architecture, which supports guided incremental change across multiple dimensions. And I just want to talk about a couple of aspects of this definition. And one of those is this idea of guided change. Part of our nomenclature that we've created for our book is this idea of an architectural fitness function, which is an objective integrity assessment of some architectural characteristic or combination of architectural characteristics. So let me give you just a couple of examples of these things. So let's say that you're an architect and you're building some sort of component-based system. One of the things that you don't want in that system are cyclic dependencies between your components, where one component references another one, which references another one, which references the original one. This is bad because now it's hard to reuse one of those in some future scenario. And so as an architect, I'd like to be able to prevent this from happening. You can do this by writing a fitness function as a unit test. This is using a tool in the Java world called JDepend. And what it does is check for cycles in your code base and will fail a unit test if one of those exists. There's a similar tool in the .NET world called Independ that does these same kind of cyclic checks. Here's another example. As an architect, let's say that you've designed an architecture, this traditional layered architecture with a presentation layer, a business layer, and a data layer, and you hand this over to developers to implement it for you. How can you make sure that they implement this architecture correctly? There's a really nice tool available now called ArcUnit that allows you to write architectural level governance rules as unit tests. And here's a good example of one of those. I'll highlight the one in the middle here. No classes that reside in a package service should access classes that reside in a package controller. Now, many of you as architects have written almost this same English sentence in a wiki or SharePoint portal somewhere, and it was right once, read never by another human being. You wrote it there to build some governance rules, but nobody's ever going to read that because there's nothing that forces them to read it. If you write it as a test, they cannot ignore it anymore. These are governance rules with teeth that nobody can ignore. So here's another example of a fitness function. Some of these rely on tools like ArcUnit, but some of these are just ways to think about solving a problem. So I was working for a large financial services company in Manhattan, and they were using a variety of open source libraries, and one of their lawyers got really concerned at one point about the license terms of some of these open source libraries. They didn't want to accidentally take on a viral license term, which would affect their ability to license their stuff. And so we chased down all the license files for all these open source libraries and frameworks and let the lawyers look at them. And then one of the lawyers asked a really awkward question. What happens if one of these libraries updates the term of their license during a software update? And we'd like to just say, well, you're just being a paranoid lawyer because that would never happen. But of course, he had a case in his back pocket where it had happened. The Qt user interface library fundamentally changed their library during a minor software update, so now this is a problem that we have to deal with. So here's how we ended up solving this problem by building a fitness function that looked at licenses for open source libraries. What we did was we knew the location for the license file in each of these libraries and frameworks. So what we did was take that entire license file, hashed it, and put that value into a database. Then anytime one of these libraries did an update, we hashed the license file, compared that to the version in the database, and if it changed, we call the lawyer. Okay, look at the new one. If that one looks okay, we'll hash it, put it in the database, and it's now the current value. And so now we're basically notified every time one of these things changes. This is true for a lot of these governance rules, because really what this is a heartbeat. It's basically something that says, it's okay, it's okay, it's okay, it's okay. Whoops, it's broken, come fix me. Okay, it's okay, it's okay, it's okay. But the problem if you don't have this is your whole life is going, is it okay? Is it okay? Is it okay? I don't know. Is it okay? Is it okay? And you never know. Having this heartbeat there is one thing you don't have to think about until you need to think about it. And you can think about it really hard, and you don't have to think about it anymore for a while. That's a lot of what automating governance is all about. So I'll leave you with one last piece, which is the other part of our definition, which talks about incremental change. And this is really this idea of building all these on these agile engineering practices like continuous integration and deployment pipelines and tools like that. It turns out this is the perfect place to execute these fitness functions once you've created them within your organization. And in fact, this gives you a kind of global reach. So one of the lessons that DevOps taught us was that at some point, a certain level of automation gives you a platform you can rest upon. And so imagine a world for just a moment where all of your projects were running a deployment pipeline, and your enterprise architects have a slot in that deployment pipeline. And maybe they can put some fitness functions in there for things like complexity or coupling or some other global concerns. And maybe your security team has a slot in that deployment pipeline as well. So now I've got a question for you. What do you do in your organization right now if you have a zero-day security exploit for one of the libraries or frameworks you're using for development? This is not a random question. This happened to a major financial institution in the US a little over a year ago, and they're still recovering from this. So what they do, they found out a zero-day exploit was in struts, and so the security people ran around the organization looking for affected projects, and they found a bunch of them. And a bunch of them fell through the cracks because they didn't have automation. What if every one of your projects was running a deployment pipeline and your security team had a slot in that deployment pipeline so that when that zero-day exploit comes out, they can insert a test in that deployment pipeline that triggers a build that says, if you're using this affected version of struts, fail your build and notify the security team. This is using automation to create a platform for governance across the entire organization so you don't have to manually run around and miss a bunch of things in an ad hoc way. So the last example I'll give you of incremental change is the ability to make small changes at the architectural level. And this is a case study from the GitHub engineering blog called Move Fast and Fix Things. And this describes a particular problem they had at GitHub about merge. Turns out since day one at GitHub, the way they've merged two things is to shell out to a shell script, tell command line git to merge them, and then suck it back into GitHub. And that works great because command line git knows how to merge things, but it doesn't scale particularly well. And these guys operate at extreme scale and also extreme agility. They do continuous deployment and they average 60 deploys a day. And so now they need to make this major structural change. And so they bit the bullet and wrote the internal memory-based merge routine and did their due diligence testing. But now here comes the scary part of my talk. Now they have to put it live. But here's the problem. You can't break merge on GitHub. It has literally worked perfectly since day one. And the last thing you want to do is start introducing regressions into something that's never been broken. This is a really common problem in architecture. How do you make structural changes without introducing side effect instabilities in a bunch of other places? The way they did this and open sourced it on your behalf is to create this tool called Scientist. And they've already ported this to a bunch of different languages. And what Scientist allows you to do is conduct experiments. So Scientist gives you a use block and a try block. The use block is the old thing we used to do, and the try block is new stuff we're trying out. And so you set the threshold for how often it executes the try block. So the merge experiment, they did the try block for 1% of the time. It always executes use, and that's what it always returns to the user, but in one case, it also executes try. It randomizes the order, measures durations, compares results, swallows and recording exceptions, and publishes all this stuff live. So they first went live. Here are the merges they were doing. So at 220, they were doing a little over 2,000 merges. If you look closely at the bottom, you can see some tiny red tick marks, which is where use and try disagreed. So I'll zoom in on the bottom. So you can see that's where try and use disagreed. But they're also measuring performance. So here's the performance graph, and the green line is the new code, and the blue line is the old one. So this is a lot more performant. They ended up running this experiment for 4 days until they had 24 hours with no mismatches or slow cases. They removed the old merge code, left the new merge code in place. No regressions whatsoever, and during that 4 days, they did more than 10 million comparisons between the old code and the new code. So they had really high confidence when they left that new code in place that it wasn't going to break anything or cause any breakages or regressions. That's a great example of incremental change at the architectural level in a safe, controlled, engineered way to make sure that you don't break stuff. So to summarize this stuff, one of the ways to support constant change is remove needless variability from your organization, because that allows you to put more effort into things that you benefit from being variable. Also, automation gives you a platform that you can rely on to do all sorts of interesting stuff. Everything is a trade-off, and if you don't think it's a trade-off, that just means you haven't identified the trade-off yet. And the best advice, of course, is constantly evolve your thinking. Don't get caught up in this is the way we've always done it. Constantly put pressure on thinking about changing the way you're thinking, because the world is going to continue to constantly change underneath you, and the faster you adapt to that, the better off you'll be. Thanks very much for coming, and hope you enjoyed it. Thanks.